We've seen previously that f of xy equals c defines a curve for any reasonably behaved function f of xy. So that f of xy equals c, where c is a constant, defines a curve in the xy plane. As a simple example, if f of xy is 3x plus y squared, then the equation f of xy equals 4 becomes 3x plus y squared equals 4, with solution y equals the square root of 4 minus 3x. And this defines what we call the c equals 4 curve for the function f of xy. And let's get this over here, we can read it. For the function f of xy equals 3x plus y squared. So this is just one example of a function being set equal to constant, giving us a curve in the xy plane. This function is called a level curve. It's a level curve for the function xy for the constant value c. Now, if we look at f of xy, if we look at any point of the graph of f of xy equals c, let's say point x naught y naught, what do we get? What is f of x naught y naught? Well, since f of xy equals c at every point on this curve, f of x naught y naught is c. Now let's take another point which we might consider to be nearby, but it could be any point on the curve whatsoever, and call this point xy. Then we know that f of xy equals c, because f of xy is equal to c for every point xy on the curve. The implication is now, if we move in the direction of the tangent vector, and let's let u be a unit tangent to the curve, so if we move in the direction of a vector u which is tangent to the curve, then for small motion along the tangent vector, we're going to move to a point that's very close to the curve, and the smaller the motion in the direction of the unit tangent vector, the closer we're going to be to a point on the curve. And it follows then that the change in f being 0 between any 2 points of the curve, we're going to be able to conclude, and we're leaving out a few details at this point, but we're going to be able to conclude that the directional derivative in the direction of u of the function f, when that directional derivative is evaluated at x naught y naught, has to be 0. So that the derivative in the direction u of f of xy is 0 for any xy on the curve. And I guess we should add where u is tangent to the curve. Now again, relying a little bit just on plausibility, the direction of the gradient of f, the direction of del f, is the direction of maximum change in f, as we've seen. So if del f is the direction in which you have the maximum change, it's going to follow that the direction of no change is perpendicular to the direction of maximum change. Now we've seen that if the direction of the unit vector u tangent to the curve is expressed as cosine theta I plus sine theta j, then if we go perpendicular to that direction, reversing the coordinates, getting the vector, let's say, negative sine theta I plus cosine theta j, we're going to end up with no change. And that should be fairly easy to understand in terms of these situations and examples that we've seen. Again, we're going to come back and do all this rigorously. So if you don't believe me now, I'll try to beat you into submission later. From this, it then follows that the direction u in which the derivative, that the directional derivative in the direction u of the function f is 0 is perpendicular to the direction of the gradient at a point. Again, not a completely rigorous statement, but take it as plausibility, and take my word for it at this point that the curve f of xy equals c as a result is at every point perpendicular to the gradient of f. to the gradient function at that point.